on functional thinking. A lot of times when you encounter these new paradigms in the functional programming world, it's also mashed in together with a bunch of details about new languages like Clojure or Scala. And now you're trying to learn two things at one time, which just makes it that much harder. And so my focus in this talk is really trying to take those functional concepts, but anchor them really, really close to the Java world. And so most of my examples here are in Java. When Java can't do it, I switch to Groovy. I think I have one Clojure example and one Scala example, but mostly I'm concentrating on the paradigm shift that comes from thinking in a more functional way. And I'm going to start with a metaphor, an essay, and a history lesson. Here's the metaphor. Let's say that you're a lumberjack and you're okay. You're the best lumberjack in the forest at cutting down trees with an axe. It's stunning how fast you can cut down trees with an axe. And then somebody comes along and hands you one of these, but they don't show you how to crank it. And so your first instinct as a lumberjack is to take the uncranked chainsaw and swing it against a tree, and very quickly reach the conclusion, chainsaws are terrible ways to cut down trees. I'm going back to the axe because it feels really good in my hand. I've been using this axe for 10 years. This axe feels awesome when I swing it. I know exactly how to swing it. Until somebody shows you how to crank one of these things, you can cut down a whole lot more trees. The point of this is the point that I made earlier, that learning a new language is easy. We've all done this a bunch of times in our careers because it's really just learning new syntax. But learning a new paradigm is really hard, and that's really what I'm trying to focus on in this talk, is trying to get this new paradigm instilled. And so my first observation is that functional is much more a way of thinking than a particular language or tool set. You can do functional programming in Java using just raw Java and with a couple of frameworks that I'll show you as we go along. Here's the essay. This is an essay by the well-known blogger Steve Agee called Execution in the Kingdom of Nouns. This was written in 2006. And in this essay, he talks about this mythical kingdom where nouns are first-class citizens, but verbs are subjugated slaves. Verbs are not allowed out by themselves. They always have to have a noun chaperone. In fact, it's gotten so bad in the kingdom of nouns that they've had to create a special kind of noun that has no actual nounness, that does nothing but carry verbs around, because you have to chaperone verbs at all times, because who knows what might happen otherwise. Of course, this land that we're talking about is Java, and this reliance that everything has to be in a class. And they quickly realized that that was kind of a silly idea, because in Java, the first version of Java, they didn't even have anonymous classes. So if you wanted to throw away a piece of code, you had to cook up a name for this made-up noun just so you could attach a verb to it. And of course, that makes perfect sense when you have a context like this, where shape has a draw method, and that makes perfect sense. But when you get to arcane stuff like this, it starts making less and less sense. We really need the ability to pass behavior around. And that's what we're really getting at there, is languages need a way to pass behavior around as well. Nouns are not quite sufficient. And so, not surprisingly, this talk is going to be largely not about nouns, but about verbs. And here's the history lesson. This is a poster you can download from O'Reilly, which is the history of computer programming languages. It only has about the top 200 on it. There are well over 2,000 programming languages that people have cooked up over the relatively short amount of time we've been doing this exercise called programming. But I want to point you back to a particular era, back in the 70s, 80s time frame, and point out a couple of events. One of them is this. Simula 67. Does anybody know the significance of Simula 67? Back in 67? Yes. Yes, first object-oriented language. Simula 67 introduced those concepts. Smalltalk came about in 71. C++ came about in 1983. Now, I think there's a robust argument to be had over drinks as to exactly when did object-oriented programming become mainstream. I don't really think it was mainstream before C++. I think that's what really pushed it into the mainstream. But the point of that is, they discovered this concept back in 1967. And that's back in the days when they were doing go-tos and unstructured jumps in code and other crazy stuff like that. We're just thinking about structured programming. And so you would think that when they saw something as insanely useful as classes and objects, they would have gone, oh yeah, that's clearly what we should be doing, not this other crazy stuff we're doing. But they didn't. It took 15 years or more for those ideas to finally seep their way into the mainstream and people start being productive and taking good advantage of those ideas. And this happens a lot of times in the computer world where you have this mainstream technology and then you have these offshoots, like academic offshoots, and functional programming was kind of one of these academic offshoots where they were experimenting with different ways of looking at problems. Artificial intelligence, another one of those. You have practical offshoots of things like XBase and 4GLs. But every once in a while, these offshoots start really bearing fruit and come and merge back into the mainstream technology branch. And I think that's what's happening now with functional programming, not just in the Java world, in the .NET world as well. F# now ships with Visual Studio as a first-class citizen of the .NET ecosystem, and it's a functional language based on the ML family of languages. If you look at the changes that are happening in most of the languages that are really active right now, in languages like Ruby and Groovy, the things that they're adding to them are all based on ideas that come from the functional programming world. So now is a good time to start learning these concepts because these concepts are invading your languages that you're using now, whether you like it or not. You don't have to switch to Scala or Clojure or F# to start doing functional programming. You can do a lot of functional programming in Ruby and Groovy and increasingly in the near future, Java and of course JavaScript. There's some really good functional programming libraries in JavaScript as well. There's a great quote that is very perceptive, and it actually shines through several of the examples that I have in this talk, and it's by Michael Feathers, the guy who's responsible for the book Working with Legacy Code. And this comes from Twitter, which is why it's a little bit terse, but it's a really good distinction that he makes, where he says that object orientation makes code understandable by encapsulating moving parts. Think about the things that you know about object-oriented imperative languages. A lot of the features are designed to either show or hide information at certain levels. From some people can see it, some people can't see it, some can see it but not change it, other people can see it and change it. The way inheritance and polymorphism, there are a lot of machinery within those languages to make it easy to see and manipulate state. That's what he's calling moving parts. Functional programming makes code understandable by minimizing moving parts. The concept being if we get rid of parts, then you can't make mistakes in those parts. If you never see them as a developer, you can't mess it up. Garbage collection is a good example of hiding a moving part from you, a very error-prone thing that makes people make a lot of mistakes on. By paving that over, they eliminated a lot of mistakes. That's an example of hiding a moving part that we used to have to deal with. And functional programming takes away some of the moving parts that we're accustomed to in the object-oriented world. So I'm going to talk about a lot of examples of code, and so I need some code and a problem to solve. And here's the problem I'm going to solve. I've solved this problem a couple of times before, and there's a really good write-up of the imperative version of this, which is one of the reasons I chose this problem. It's a problem of number classification. So any whole positive integer can be classified in one of three ways. And here's the first of them. It's a perfect number if the sum of the factors of the number minus the number equals the number itself. Another way to say that's the sum of the factors of a number is equal to 2 times the number. 6 is a perfect number because if you take its factors and add them up, it equals twice 6. So is 28 and so is 496. Those are all perfect numbers. So that's how you determine if a number is a perfect number or not. And that's actually the key to this classification scheme. If the sum of the factors is equals to 2 times the number, it's perfect. If it's greater than 2 times the number, it's abundant. If it's less than 2 times the number, it's deficient. So I want to write some code that, given some number, tell me which of these 3 categories it lives in. I'm going to start with an imperative version of this code. And one of the reasons I chose this example is I'm not going to go into a lot of detail as to why the imperative version of this code looks exactly the way it does. If you want to read that description, it is actually the sample chapter of my Productive Programmer book, because this example was written to illustrate test-driven development. And so the test-driven design chapter uses this exact same example and shows you the thinking that went into the shape of the imperative version. I'm just going to show it to you relatively quickly. So here's my imperative perfect number finder. The first thing I do is create some shared state. Some of this is to make testability easier, and some of it is to do lazy initialization for sums. I initialize all these guys in a constructor. My isFactor method is really one of the key little pieces of this algorithm, because what it does is say, well, give me a factor and a number if I can say number mod factor equals 0, that means factor goes into a number with 0 remainder. It is one of the factors, so I can determine a factor that way. I then have a calculate factors that goes through and does a loop up to the square root of the number. And there's a little bit of an optimization at work here, because a really common way to make this algorithm efficient, consider for a second if you were trying to determine the factors from number 16. Notice that factors always come in pairs, because it's always the product of two factors which equals your target number. So if your target number is 16, when you grab 2, you can also grab 8, because it's the symmetrical factor that equals your target number, which means I don't have to loop all the way up to the number if I'm trying to find factors. I really only have to go as far as the square root of the number if I harvest those factors in pairs. And that's exactly what I'm doing. I loop up to the square root, and when I grab one of them, I come down here and add both the number and its symmetrical factor to make this faster. It's a very common, significant optimization for this code. Here is my sum factors, and you'll notice I have a getSum method that is basically doing lazy initialization for me. The anticipated use of this class is going to be, I'm going to call this perfect. If it's not perfect, I'm going to call one of the others so I can classify this thing. I don't want to have to calculate that sum over and over, so I'm only calculating the sum once, so I'm lazily initializing that. So the first time through it gets initialized, and then other times I don't have to do it for a given particular number. So that's one of the reasons I have that shared state there. So more than the details of the code, I'm really interested in kind of the shape of the code. So you'll notice this has internal state. It has internal state for two reasons. One, to make it much easier to do testing, because it's easier to inject things when you're doing testing, and so that's part of why some of the internal state is there. The other is to enable this lazy initialization behavior. This code is very cohesive in that it's lots of very small single-purpose methods. It follows the kind of Kent-Beck compose method style of coding. It's very testable. In fact, it was created as an illustration of testability. And it's also very refactorable because it is lots of very small methods. And my goal in creating that code was primarily to illustrate how things can be very, very testable by being very, very cohesive. But what if I went into it with additional criteria as well? Like, I want to minimize shared state, which is one of the goals that you see a lot in functional programming. I still want to maintain the testability, but I'd like to chase away some of the shared state. So here's a slightly more functional version of the same code, still in Java, but with a different perspective in mind. And so now in my getFactors method, I actually do the work of 3 different methods for my imperative version. I've collapsed all those together so that I can own factors as a local internal variable here. So factors lives entirely within here. I'm still doing my little optimization here, but this is now split and consolidated into one method. And now for my isPerfect, isAbundant, and isDeficient code, I now have gotten rid of the shared state, but I've now lost my optimization. Now, if I call this more than once, it's going to do the sum every time. That's one of the side effects of losing that shared state. I was holding on to a useful thing in that shared state. If I'm trying to minimize that, then I'm going to take a performance hit from doing this. But that's a trade-off, and in fact, in a bit, we'll come back for this version and make it just as good in a slightly different way. But when you look at this code, you'll notice there's no internal state anywhere in this code, which means there's less need for scoping. If I don't have any internal state, there's no compelling reason to make things private because there's nothing really to hide in here. In fact, there's some real nice benefits of making these methods public, because that get me the factors of a number method. If I'm trying to find prime numbers, that would be a handy method to have, and so I made them all static and public. So now I can say number classifier dot factors, and now get factors for number for other purposes. We actually, in the Java world, a lot of times don't think of reusability at the function or method level because it's been so beat into us that reusability always happens at the class level. But you can get reusability at a much lower level as well. This code is still testable. In fact, it's still done test-driven development like the other code. It's still very refactorable, but of course we've lost our lazy initialization for now. We'll restore that in a really nice way here in just a bit. And so this goes back to my contention that functional is more a way of thinking than a particular tool set or a particular language. You can do more functional style coding in Java if you emphasize some of the things that functional programming tries to emphasize, like minimizing shared state. So one of the things that you'll find as you start looking into functional programming, it is a pretty deep and broad ocean. And there are all sorts of really fascinating little inlets that you can find yourself kind of wandering down. A bunch of really fascinating stuff about category theory and a lot of theoretical stuff. And so what I wanted to do is go grab some concepts that kind of relate to us in one way or another and show you a few examples of some of these concepts in action. And one of those concepts that's going to be very near and dear to our heart very soon is this concept of a first class or higher order function. These terms are basically interchangeable. One is a computer science-y term and the other is a mathematics kind of term. But they both essentially mean functions as first-class citizens. Can be passed as parameters, can be return values of functions. And we're going to get this in Java 7. That's what the Lambda stuff in Java 7 is going to give us our first-class functions finally. Pure functions are ones that have no side effects outside themselves. In fact, the functional, slightly more functional version I just showed you was a bunch of pure functions because they rely only on their parameters and nothing else. And your runtime can do some really nice optimizations if you have a lot of pure functions. Recursion is something that we don't really think of much in the Java world because the JVM was never really particularly suited for doing a lot of recursion. And so Scala and Clojure have had to kind of solve this problem themselves within the language. But it does give you some really nice benefits in terms of eliminating state. A lot of times you can get rid of iteration variables and things like that by using recursion instead of keeping an iterator going. And another one of these concepts that's slightly academic is this idea of strict evaluation, but it leads to this really useful concept in a lot of functional programming languages of laziness and being able to create lazy sequences of things. In fact, in Clojure, for example, all the collections try to be as lazy as possible, meaning it doesn't try to pre-calculate all the values in the collection. It only calculates as many as you need right now, and then we'll calculate the new ones on the fly. And so it tries to do as little work as possible by creating what look like infinite collections, but you just keep asking for more values. So let's talk about a few of these and show deeper examples. And I mentioned this idea of higher order functions, which are functions that can either take other functions as arguments or return them as results. This is the this is a mathematics definition of this. And this is a really, really common need in our world. In fact, you bump into this kind of scenario a lot. I showed this code in my Agile Architecture and Design talk yesterday. This was actually the target of a refactoring exercise where I got it down to a point where I had discovered essentially some reusable code here, because if you replace these two lines with something different, what I basically got is a template for doing transactional data access. And so the way that you would harvest this, if you wanted to save this in your code base to make use of this later, this template that you've created, is to apply a gang of 4 design pattern to it, something like the command design pattern. And so what you do is you create this wrap-in transaction that takes in a command, you execute the command there, and then down here you change your add order method to wrap-in transaction, create a new command with this execute method and the little pieces of work that you want to do. But of course, this is just a cry for help for portable code, because that's all we're really doing here. That's all the command design pattern is a band-aid for the fact that Java doesn't have a way to pass around code. Command is literally just this noun that has no real purpose in life except as a holder, as a chaperone for verbs being passed around. And so if you go to a language that supports higher order functions, like Groovy, this code becomes a lot better and prettier. Because this is the same code in Groovy, but here code blocks are a first-class citizen in the language, and anything in curly braces is a code block, and you can pass this, and if you want to execute a code block in Groovy, you can either call the .execute method on it, or you can use the syntactic sugar of the open and close parens, and it'll execute that code block that you're pointing to. That actually gets rid of a lot of boilerplate and a bunch of other stuff that's really not technically necessary. It's just there because the Java language doesn't have this facility yet. But the other thing that's interesting about this code block in Groovy and the way that code blocks are implemented in most functional languages is that it's not just a code block, it's also a closure. And you hear a lot of things about closures, and so I wanted to give you an illustration of what's so cool and special about closures. And I can't do this in Java, of course, because it doesn't support closures, but I wanted to cook up the simplest example I could that illustrates this concept in a Java-like language, so I did it in Groovy. So let's see how well I did. So let's see what this code does. So this is a method called makeCounter. And what it does is define a local variable called veryLocalVariable and initialize it to 0. And then it returns a code block. Ignore what the code block does for a second. Notice that anything in curly braces in Groovy is a code block, so it returns a code block. So when I say C1 is equal to makeCounter, C1 is now pointing to an instance of that code block. And if I want to execute that code block, I can execute it like that. And when I execute that code block, what it's going to say is a veryLocalVariable is equal to veryLocalVariable plus 1, so it's incrementing veryLocalVariable. And in Groovy, the last line of any code block is the return value of the code block. And so the return value of this guy is going to be whatever the value of veryLocalVariable is. And so if I looked at the return value here, it'd be 1. And here it'd be 2, and here it'd be 3. Then I come along and say C2 is equal to makeCounter. I now have 2 instances of that code block. If you look at this underneath in Groovy code, I have fired the constructor on 2 Clojure classes that are holding on to this stuff now. But now when I come down here and say print out C1 and C2, when I print out C1 I get 4, when I print out C2 I get 1. And here's the magic special thing about closures. Because technically veryLocalVariable is out of scope by the time this function ends. But because I create a code block right here, by putting that in curly braces, I instantiate a new code block. It's a closure because it encloses the environment that is in place when that closure block has been instantiated. So it keeps its own version of veryLocalVariable unique to C1 so that you can increment it across calls to this method. It doesn't reset that variable to 0 every time because it's now captured in that closure block. That's why they're called closures. It encloses the environment that was in place when it got instantiated, and now it can carry that environment around with its own instance of it until such time as the closure block itself gets garbage collected and all that stuff goes away. This is a great example of a functional language hiding state from you, hiding moving parts, because that state that you have to maintain is a moving part that you have to maintain by hand in the Java world. Functional languages do this because it's really nice to have code blocks that can have values that live beyond a single invocation so that you can do sums and a lot of other useful things with them. And so this is an example of letting the language manage that state for us rather than having to do it by hand. And in fact, this is one of the reasons why you should be interested in functional programming right now. Because over time, we're seeding more and more busy work to our languages and our runtimes. Like memory allocation. I don't know about you guys, but I never want to work in a non-garbage collected language again. Been there, done that, got the t-shirt, life is just too short for malloc. It just is. It's just too much of a pain in the ass to deal with. I've got better things to solve than chasing down pointer errors and junk like that. So I thought the advent of garbage collection was awesome. I love that feature, and I never want to give it up. But over time, we're seeding more and more of our busy work to languages and runtimes. Like concurrency, Clojure basically does for concurrency what Java did for garbage collection, in that it takes over the assignment semantic, and now you don't have to worry about threading anymore because that's just a part of the features of the runtime. You're seeing more and more things hiding state. Even things like tests, there's some really interesting specification-based testing stuff going on in the functional programming world that can write some really, really intelligent tests for you. And so all of these things that we're seeing now, we're seeing because our runtimes finally have enough excess capacity to deal with these things. So back in the early 1980s, I was in a university and we were using a piece of software called Pecan Pascal. And it had this crazy characteristic that it would run on an IBM PC and an Apple II by using this crazy technology they called bytecode. And when you compiled your Pascal code, it compiled to bytecode. And then they had a bytecode interpreter that ran on each of those computers. And it was a pig in terms of performance. I mean, it was so slow, it was ridiculous. We were trying to write hello world programs, and it was too slow to be useful. Because the runtime just didn't have enough horsepower to handle bytecode interpretation at runtime. But then you fast forward a decade, and Java comes out, and they use that same approach, and the runtimes are enough to handle that extra overhead of garbage collection, bytecode interpretation. It's exactly what we're seeing with a lot of these functional concepts like map, reduce, and those other concepts. Our runtimes now have enough excess capacity that it's actually foolish for us to waste mental capacity on solving these problems that computers can just solve almost invisibly for us now. And so over time, this happens more and more, and the time is starting to come for a lot of these functional concepts to make it into mainstream languages and runtimes. So as I'm talking about first-class functions, this is actually the computer science, typical computer science definition. Function can appear anywhere any other language construct can appear. And of course, we don't have that quite in Java yet, but we can get close. Using a library called functional Java. This is a library that's been around for a little while. It's currently in version 2.x, 2.8, I think is its current version. What it tries to do is give you as much functional programming capability in Java as it can without changing the language. So they use generics a lot to mimic code blocks. It's a pretty nice library in that it doesn't take an entire Maven's worth of jar files to make it run. It's a single jar file. As long as you have a Java 1.5 or higher and this single jar file, you can use functional Java. So what I'm going to do is use functional Java and rewrite my number classifier using some of these functional programming techniques. And here it is. So let's look at some of the changes. Here's the first one in sum. Because sum now, if you remember, used to iterate over the list of all the factors and sum each one of them up. And so what sum does now is say return factors.foldLeft add comma 0. How is that summing something? Well, so let's pull some of this apart. First of all, notice this is not a Java list. This is a functional Java list because there's no fold left on a Java list. So this is one from the functional Java world. And that add guy is actually an enumeration that's also defined in the functional Java world. So there's the entire namespace for it. That's an add, little add function. Here's what's going on. So think about a list of numbers for a second. What a fold does is say, okay, I want to convert that list of numbers into a single value. And the way that I'm going to do that is take the second element and fold it in on the first element, but I need to know what function to apply as this fold operation. In other words, I need to take two numbers and convert them to one number. You do that with an operator, and the operator I'm going to use is add. So I'm going to add the second one to the first one, and then I'm going to add what is now the new second one to the new first one, and keep doing that over and over. That's what a fold operation does. And I'm folding using add, so that when I'm done with this, what I have left is the sum of the list. That's a fold in the functional programming world. And that's exactly what I'm doing here with, to get my sum of my factors. I just say factors fold left, and I get a sum. And given that there's a fold left, you can also guess there's a fold right. It doesn't matter for plus if you fold left or right, but some operators like minus and divide have a order preference, and so a fold right is if you wanted to subtract them all toward the end, you could do a fold right. There are a bunch of these enumerations that have been predefined for you in functional Java, particularly for mathematical kinds of things. You can write your own code blocks and insert in there, and I'll show you an example of that in a second when we do filtering. This has to be kind of bolted onto Java, of course, because through a framework, but this is really natural in languages that support this natively. This is the exact same code in Clojure, a sum factors method, function that takes in a number as a parameter. And this is being a list, so you kind of read inside out. Factors of numbers, a function call that returns the list of all the factors. Reduce is just a synonym for fold left. It's reducing the list. And plus is the method that I'm using to contract to fold that list down. In Clojure, operators are just methods with odd-looking names, and so plus is just the method name for the add operator in the Clojure world. This is a good example of another one of these kind of core concepts in the functional programming world, this idea of using fold left. And that is to think about results, not about the steps required to get to those results. Now, I'm not for one moment going to suggest that SQL is a functional programming language. It's actually a weird amalgam of a bunch of different paradigms, but it does share one interesting characteristic in that when you issue a SQL query, you generally don't go and tell it how to allocate memory on the database server and where on its file system go find these records and put them together. No, you just say, I want these results, and you go get them. And what we're trying to do in the functional programming world is add some of that same kind of capability at the language level. You don't have to worry about iteration, say, here's the results I want, you figure out the most efficient way to do this. And in fact, the nice thing about this is once you turn this over to machinery, there's a really cool thing that Rich Hickey's talking about this year, where he has optimized the way that some of these mechanisms work in Clojure so that you can automatically get parallel behavior in some of its list operations in Clojure. Because you're using these higher order functions and not trying to iterate by hand, the runtime can actually make some really intelligent decisions about optimization that you don't even see. They just kind of happen automatically. So that's one of the original problems I had to solve, which was how to do a sum of numbers. Let's see if we can attack another one of those problems in a functional way. And that is how to find the factors of a number. So let's say 12 is my number in question. I need to get the factors of 12, but I don't want to do iteration. How can I do that? Well, the first thing you can do is observe that it's going to be some of these numbers, but probably not all of them. These are all the possible factors of 12. I'm guessing that not all of them are factors of 12. It's only some of them, which suggests a filtering operation. I need to take that entire set of numbers and filter down to just the ones that are factors of 12, which is exactly what this code does. Factors of takes in a number. It then returns a range from 1 to number plus 1, because ranges are non-inclusive in functional Java, dot filter. Filter takes in a code block that uses this class in functional Java. There's a capital F class that has an F method that stands in for a code block, and you can use generics to satisfy the type system. So here what I need is a function that takes an integer and returns a Boolean, and I'll create that as an anonymous inner class like this, and you'll notice what I'm returning there is my isFactor method that I created before. So what this is going to do is for every element in the list, it's going to apply this filter method, and only the ones that return true for isFactor are going to make it in this returned list. So it's filtering down my list to give me only the numbers that are factors of 12. But is this as efficient as the hand-tuned imperative version that we saw? Not even close. Because this is going to touch every number. Remember in the imperative version, I'd gone in and did that square root optimization to make it much more efficient, and I've lost that here. Sometimes when you cede control to runtimes, you lose some of that control. I'll actually come and grab this control back in just a bit, but notice there's a trade-off there. We can also fix this in a functional way, which I'll do in just a bit. But this is what my functional Java version of my number classifier looks, thinking about results rather than thinking about steps. So next I want to talk a little bit about pure functions, which are functions that have no memory or I/O side effects. And when you have pure functions, your runtime can do some really useful things with it, because if the result isn't used anywhere, the runtime can just strip the entire code out of your runtime. You can also get parallel execution automatically by the runtime, which means that it can also change the execution order because you don't rely on external state. It doesn't matter what execution order happens. And all those are kind of optimizations that the runtime can handle for you. But here's the really cool one. Notice that if you have a function that only relies on its parameters, every time you call it with a certain value, past the first time you call it with a certain parameter, the results are just going to be the same. It's going to be a constant result. So for example, math.sign in Java is a pure function. When you call sign of 90, then you know that you're always going to get the same value back. It's not like that one time you call sign of 90, you get one value back, and another time you get another one. So if you thought that you were going to use the sign of 90 a lot, you could actually cache that and say every time you want this value, oh, just automatically return it from the cache. A particular invocation with a particular set of parameters yields a constant value. And runtimes can start taking advantage of this with a feature called memoization. So let me show you what I mean by this. So here's a really terse, perfect number classifier written in Groovy using a bunch of this functional stuff that I've been talking about. So there is my is factor. That hasn't really changed. Factors of, this is the terser Groovy version, 1 to number. That gives you a range. Find all, and it's using my is factor. And so this is the same as my filter method I was using before. And now in the Groovy world, instead of reduce, they call it inject, but it does the exact same thing. So factors of number dot inject, using 0 as the starting value, and this is the code block that you apply to collapse 2 elements into a single element, which I'm adding them together with plus. And then there's my is perfect, is abundant, is deficient. So this is a Groovy version of the number classifier where every method is down to a one-liner. But let's say that I have this, and I realize that I end up calling sum a lot. I try to classify the same numbers a lot in my problem domain, so I end up summing the same numbers a bunch of times. And that's really inefficient, so what I want to do is cache that sum. So every time I sum a particular number, save that in the cache, so I won't have to do it again. And so in Groovy, you create a hash map like that, and now my sum of factors says, well, if I have already summed this one before, return it, otherwise do the calculation, sum it, and then add it to my cache. But Groovy, since 1.8.4, which is about 6 or 8 months old now, has this feature called memoize. And so if this is a pure function, if sum factors is a pure function, which it is, I can now come down here and say sum of factors is equal to sum factors dot memoize. And I am done. Now the runtime caches those values for me. That hand-crafted cache that I created is useless now, because the runtime is doing this. In fact, I'll point you to, I've written up a bunch of these observations in an article series I'm writing for IBM Developer Works. And I wrote, several installments ago, I wrote this article about memoization. As hard as I could not write any caching code that beat the runtime's memoization code. And you can also tweak this cache. You can say memoize at most this number of elements, memoize at least this number. You can do a bunch of tweaking for the internal cache that memoize uses. This is a great example of eliminating moving parts, because now you don't have to handwrite a cache anymore. If you have something that's used a lot, you just say, oh, that's used a lot, memoize it, and shazam, you're done. Remember back over here in my slightly more functional version of my number classifier, and one of the things I was lamenting was the fact that I'd lost my lazy initialization. But that guy's a pure function, so I could memoize that guy and get my lazy initialization back. Great example of eliminating moving parts, handcrafted code that you don't have to write because the runtime can do it for you. So as nice as it is to seed things to the runtime, sometimes you want to get that control back. What about things that you want to control, like, for example, performance or optimization? Notice that even database servers let you do this. I was using it as a metaphor before. A lot of times you can go in and hand tune the optimization plan for a database server. You can kind of do the same thing here, but it's just a set of new different tools. So you remember over in my imperative number classifier, one of the things I did was optimized it by using the square root trick. But in my functional Java version, I'd lost that. So let's go get it back. Here's an optimize factors in functional Java world. What I have to do is attack this problem differently. I have to partition the problem myself. So what I'm going to do is say, give me the factors. I'm going to create an intermediate variable called factors, which has the range from 1 to the square root plus 1. Remember, ranges are non-inclusive in functional Java. And I'm going to filter those to get me the factors. And so what I'm getting with that first chunk of code are all the factors up to the square root. Then the second line of code in this method says return factors.append. So I'm going to append onto the list I have some other factors, some other numbers, and the numbers I'm going to append are factors.map. We haven't seen map before. This is another one of those list transformations. What map does is apply this function to every element in the collection and giving you a new collection when it's done. So it's basically going to take whatever function I pass in and apply it to each element in the collection. My collection are the factors below the square root. The code that I'm applying to each one of those is say, give me the number above the square root. So it's the symmetrical factor, the div versus the mod of that. And so what I'm doing is tagging on the remaining factors onto the end of the list by doing that. So I'm basically going and harvesting the two sets of factors in pairs. Or harvesting in, not in pairs, but in serially to get the pairs. And the last line here is this nub. What nub does is remove duplications. Basically turning a list into a set. I would have done the entire thing on the back of sets in functional Java, but they don't have the same set of methods on sets. This is actually better done on sets, just to automatically get rid of the duplications, but nub basically converts it to a set when you're done. There's an edge case here for whole number square root that you have to watch out for, but nub handles that very nicely. Good example of thinking about results, not about steps. Thinking about the problem slightly differently, but still getting the same kind of optimization. So let's talk next about concurrency. Because it's probably one of the really cool things you've heard about these functional programming languages is that they have a much better concurrency story than kind of raw Java does, and that's absolutely true. In fact, there's a great keynote that I encourage you to watch. There's actually going to be a keynote by Rich later today, and I encourage you to watch that one too. But there was a keynote at Strange Loop last year in St. Louis called Simple Made Easy that Rich did. And he explains some of the philosophy behind Clojure. It makes you realize that Clojure is more of a vision for software development that you could only really implement by writing a new language. While I was looking at this picture for Rich, I also found this funny picture of Rich, and that's a very Rich-like statement. State you're doing it wrong, because he doesn't like a very mutable state. And one of the things that Rich did was figure out what makes threading so hard in Java. And it turns out it's variables. Because when they created Java, they didn't really think about concurrency when they were creating variables. They created variables and all that mechanism, and they said, oh, we may need to run this in threads. We need to layer on some threading stuff on top of this. But variables assume one thread of control and one timeline. They're also not atomic. You can't say, make sure that these two variables get set or neither of them get set. There's no kind of transactionality around them. It's hard to compose them. They have very subtle visibility rules. And with concurrency primitives in Java, you're pretty much at lock and pray. It's just not a very elegant way of doing concurrent code in Java. If you think that you know how to do it, you should read Java Concurrency in Practice by Brian Getz, who will convince you that you've been doing it wrong all along. It's a way harder problem than you ever thought it was. And really the core of the problem here is variables. The problem is that the concept of variable in Java conflates too much on top of it. Because in Java, the identity and the value are kind of inextricably tied together in this one thing we call a variable. And it's really hard to logic about that because at any given time, its identity and value may change, which is really tough to do reasoning about, particularly in a scenario where you've got multiple things trying to address it at any given time. What Rich did was say, you know what, I can fix the concurrency problem in Java, but you have to give me something. Let me handle all of your variable assignments. If you'll let me take over that semantic, then I'll make all your threading problems go away. And so that's what he did in Clojure. In Clojure, there's really only one mutable thing, and it's a reference to something. And a reference never goes away, but the value that it points to may change. So he's basically taken the concept of a variable and split it into two pieces, an identity, which never changes, and the value that it's pointing to, which may change at some point in time. So at a given point in time, the identity points to a value. You may update it, which means that it now points to a different value. Clojure has a very explicit semantic to control that, and if they can control that, then they can handle the threading concurrency issues for you. This is software transactional memory. So when you update a reference in Clojure, it always happens inside a transaction and handles all these threading concerns for you. So basically what Rich has done, and he's going to do that with values today, he's on a campaign to add temporality to the computer science world, and it's long overdue because he makes a really good point that nothing makes sense without a timestamp. Even a fact like the sky is blue. No, it's not. It's blue between certain times of the day. You can't make universal facts about things without supplying some sort of temporal context to them almost always. And we don't do that in programming languages much. So in the Clojure world, a value is an immutable data in a persistent data structure somewhere. Identity is a series of causally related values over time. The identity points to values that may change over time, but the identity doesn't change. State is identity at a given point in time. And time is relative before, after, simultaneous ordering of events. And so what happens in the Clojure world is identity is a succession of states that moves from one state to another by applying pure functions to move it from one state to another. That's how you update things, through pure functions. At some point, some observer, some other program, or some user, or somebody is going to look at that identity and dereference it and find out what its value is. At that point in time, that is its state. At a given point in time, the value pointed to by an identity is its state. The other thing that Clojure does is give you a way to consolidate variable access and give you basically ACID characteristics around variables. In fact, it's almost ACID. So in the transactional world, you talk about atomic, consistent, isolated, and durable. We have ACI. We don't have durable because this all happens in memory. But we do have atomic, consistent, and what is it? Well, the ACI. I just said them a second ago. Now I can't remember what they are. Atomic, consistent, isolated, across several different variables. And the underlying mechanism is kind of sophisticated, but the syntax for doing it is very quite simple. So in the Clojure world, if I wanted to create a reference, let's say I want to keep track of a list of messages. Let's say I'm creating a chat application. I want to create a list of messages. The way that I do that is define a messages variable, and it points to a reference that is a reference to an empty list right now. So that's an identity, and the initial value there is just an empty list. I can now dereference that reference at any time that I want to by calling the deref function on it, which now gives me an empty list because I don't have any messages in it. There's also syntactic sugar in Clojure to say @messages, which does the same as doing a deref. If I want to alter a message, I can call an alter function, give it the old value, and an update function. And what it'll do is move this from the old value pointing to the new value by applying this, whatever this update function is. And so here's what this looks like if I was actually adding a message to my message list. This is an AdMessage function that takes in a message. And what it says is alter the messages list and conjoin the new message onto the end of it. That's basically what that line of code says. But you'll also notice do sync over here. Because this guy is a reference, the only way you can update that guy is within a transaction in Clojure. That's the only way you can mutate references is within a transaction. If you try to execute this code without do sync being there, the Clojure runtime will actually throw an exception at you that you're trying to update a reference outside a transaction, which is not allowed in Clojure. But by doing that, he has now created a scenario where you can write multi-threaded code. You never have to worry about deadlocks. There are no race conditions. Writers never block readers. And basically all the things that you have to craft by hand just kind of go away. And so because he's taken over concurrency, he can also do a lot of really nice things around optimization at the language level that just automatically makes things better for you without you having to do anything, because now, just like garbage collection is sunk down to the level of the platform, so is concurrency. This is very ambitious. In fact, several other languages have tried to create STM. Haskell very famously has software transactional memory. They tried it in C# and then abandoned the effort a few years ago, because trying to create software transactional memory in a place that is rife with mutable state is just too impossibly complex to do. Haskell can do it because they favor immutability, so can Clojure. So it's a really, really sophisticated mechanism that it requires rethinking some core things at the language level to make work. And so that's how Clojure is possible to do this, and why it's very difficult to do in other languages that weren't written with this in mind from the ground up. So Clojure is very ambitious, and they've basically rewritten a lot of your basic assumptions about the world. Scala is not trying to be quite that ambitious, and what they're trying to do is build a bridge from the kind of world that you know into the functional world, and paving it a little more nicely for people who are used to object-oriented imperative code. And so what Scala has done, one of the nice concurrent features that they've added is this idea of actors. Which is much closer to the kind of a Java model without having to worry about synchronized blocks and things like that. So here's an example. This one only does perfect numbers, but notice that if you've got a number like 16, for example, and you had 4 processors on your machine, when you're trying to determine if if a particular number is a factor, those can all run in parallel. So you could say, you know what, processor 1, you handle number 1 through 4 and see if any of those are factors, and processor 2, you handle 5 through 8, and you can partition it up that way because none of these things are dependent on one another. So that's what I'm going to do with actors in Scala. So I'll go up here and create a parallel perfect number finder, create a range of values of this is going to be how many partitions I want to have, which may be a number of CPUs or something like that. And now for each one of those partitions, I'll create the lower and upper range by partitioning my space, and then create an actor. And so it's going to do this for each one of these ranges. And inside this actor, I can create variables that are local to this actor, but can also be used as accumulators. And so here what I'm doing is going through each one of the ones in my partial, and if J goes into candidate with 0 remainder, add it to partial sum. And now I'm messaging this partial sum back to who launched the actor. This is using kind of the Erlang message passing model for concurrency. And so a little bit further down, I kick off all these actors by saying, while I've got responses expected, start receiving these messages. And when you receive a partial sum, you gather it up, add it to the sum that I'm building, decrement the number of responses I'm expecting. When I've got them all, then the return of this thing ultimately is does sum equal 2 times the candidate, which is my criteria for is it a perfect number or not. So I could actually make this a little more elaborate and handle all the classification scenarios, but this one just handles perfect numbers, but it does so spreading across all the possible processors. So it's a different way, it's a way of doing concurrency in a new, different way, and it's another great example of hiding moving parts. All the synchronized blocks and all this other coordination that you'd have to do if you were trying to write this in Java or Groovy have now gone away because this actor abstraction has hidden all those details from you. And you can actually call actors from the Java world by calling Akka, which is the framework on top of that actors library. So I've just got a couple of minutes left, so I want to leave you with some thoughts about how you can start doing this yourself. How is this going to apply to your day job when you go back to work on Monday? You can already start moving in this direction a little bit. Start thinking about immutability over state transitions. There's actually a great article here by Brian Getz about the benefits of immutability in the Java world, and there are some extreme benefits, including automatic thread safety and this thing that Josh Block calls failure atomicity, because there's a rule in Java that constructors never throw exceptions. You either get a real instantiated object back or you get null back. And if you have an immutable object, if you get an object back, you know that it will never fail because of any kind of update scenario, because you can only set its state in the constructor. So you know that there's no way that it's going to be in a failure state after that because you can't change any part of it after that. A fun way to find out how much you rely on state transitions in your code is to go back and in your code base do a global search and replace and find the word private and change it to private final, and then try to compile your code. You'll get what I call your mutability score. How many places are you mutating things? And you can start chasing a few of those away. Of course, in the Java world, immutability is kind of a foreign concept, and so virtually none of the frameworks and tools like Hibernate and ORMs don't really support that very nicely, but certainly for little value objects, things like that, you can make them immutable and you get some definite benefits from the runtime from doing that. Start thinking about results over steps. The next time you start to write an iterator for something or iterate through a loop, think about, now how would I do this if I couldn't iterate over it? That's one way to start thinking about how can I apply some sort of higher order function to this problem and try to attack it. And try to think about composition over structure. This is one of the kind of sub-observations that happens through the course of this talk, in that In the object-oriented world, the way that we try to solve problems is to write class diagrams and then save off useful class diagrams. The design patterns book, every single example comes with a class diagram, because that's the way you solve problems, is networks of classes. That's not the way that they solve problems typically in the functional programming world, where they really want a very few data structures and a lot of operations on those few data structures. So lists, sets, maps, a few very simple core data structures, and they build really hyper-optimized machinery for those core data structures and make those really fast. And they expect you to send in data plus customization in terms of higher order functions, and then let the optimized machinery handle that stuff. It's all actually based on category theory and a bunch of really fascinating mathematics, but that's the way that they're trying to achieve reuse, is in a more generic way. And notice a lot of this, results over steps, is really declarative over imperative code. And one of the places that you see that a lot are things like domain-specific languages, which a lot of people associate with dynamic programming languages, but both Scala and Clojure are really good first-class citizens in terms of being able to write DSLs in them. One of the stated design goals of Scala, in fact, was to be a good host for DSLs, and it is a very good host for DSLs, even though it has very strong static typing. A lot of the type inferencing makes that go away and makes for very nice, elegant DSLs. So to summarize, going functional gives you new ways of thinking about old problems. More and more you can seed control to languages and runtimes, and mostly these are things you would like to seed control for because it's just too hard to get correct, or there's no huge benefit of getting it correct. I mean, you can write thread correct code in Java if you're very, very attention oriented and you go and find every single place that you might have thread deadlocks and other stuff. But life's just too short for that. You know, you could chase down memory pointer bugs all day long too, but that's not actually making your purchasing order system get out the door any faster. So there are some immediately beneficial starting steps, because if you start poking around in the languages you're using now, they're adding functional constructs at a breakneck pace, particularly languages that are evolving more quickly like Groovy and Ruby, but even Java, we're going to get higher order functions in the next release, so even Java is coming along. So this is very much aligned with language trends and pretty much across the map. And these new capabilities give you new ways of thinking about problems. Some of the problems you don't attack now because they're just too impossibly daunting to think about from a concurrency standpoint, but if that problem goes away, then you can start thinking at a higher level of abstraction. You may actually attack problems that you would have been reluctant to attack before. I alluded to this earlier, but if you want more details about this, I've been writing this article series for IBM Developer Works for 1.5 years now. In fact, today I just published installment 14 of this article series called Functional Thinking on Developer Works. It's a free site. You don't have to do a sign-in or anything. That's the table of contents for all of the series, and each one of them are numbered accordingly. Just about out of time, but do I have questions? Probably got time for a question before we take a break. Okay, well, looks like I'm about out of time. I'll be around the rest of the day today and tomorrow if you've got any questions. Happy to answer them for you. Thanks for coming. Hope you enjoyed it. Thanks.